My name is Kesha, and I'll be presenting our work on extending the VOQC toolkit. VOQC is a verified optimizer for quantum circuits. It is verified in the sense that we have formal proofs in the Coq proof assistant that the output of a VOQC transformation will be semantically equivalent to its input. So VOQC transformations don't introduce bugs. VOQC takes as input quantum circuits written in the Squire language, which is a list of gates format similar to OpenChasm. VOQC and Squire were presented earlier this year at POPL 2021, and we have a paper to appear at ITP that looks at using Squire as a source language for expressing and verifying quantum algorithms. Here's a rough diagram of the VOQC workflow. We start with an OpenChasm circuit, which we translate to Squire. VOQC performs a series of transformations on the Squire circuit, such as gate decomposition, optimization, and circuit mapping, eventually producing a new Squire circuit, which is converted back to OpenChasm. For every transformation, we prove that the input and output Squire circuits are equivalent. We also prove some transformation-specific properties. For example, we prove that gate decomposition produces a circuit that uses only the desired gates, and that the output of circuit mapping satisfies the relevant architecture connectivity constraints. In this talk, I'll discuss some recent extensions we've made to VOQC, including support for new gate sets and optimizations, better support for composing optimizations and gate and circuit mapping, and a new Python wrapper. One of the new gate sets we've added is what we call the IBM gate set, based on the default gate set used in IBM's QuizKit compiler. The IBM gate set consists of 3 single qubit gates and the standard controlled knot, or CX gate. The U1, U2, and U3 single qubit gates are parameterized by real rotation angles, and their behavior is described by the matrices shown on the slide. One simple optimization of this gate set, called Optimize 1Q gates in QuizKit, merges all adjacent single qubit gates into a single gate. The rules for combining U1 and U2 gates are simple. They involve adding certain rotation angles. The rule for combining U3 gates is a little more complicated. In order to combine 2 U3 gates, we first rewrite both gates as a sequence of Y and Z axis rotations, Ry and Rz. Next, we combine the innermost adjacent Z-axis rotations by adding their parameters. We then convert the internal YZ-Y axis rotation to a ZYZ axis rotation. Finally, we again combine the adjacent Z-axis rotations, and we're left with a ZYZ axis rotation, which represents a single U3 gate. The trick here is converting a YZY axis rotation to a ZYZ axis rotation. Defining this function takes a little over 20 lines in our Coq development and involves a variety of trigonometric functions. Its proof of correctness in our development is about 1,500 lines. In total, VOQC supports 3 gate sets: the RZQ gate set used in our POPL paper, the IBM gate set described here, and a full gate set that includes every single qubit gate we could think of, plus some additional 2 and 3 qubit gates. We also support semantics-preserving conversion between each of these sets. VOQC supports 5 optimization passes over the RZQ gate set and 2 over the IBM gate set. Finally, VOQC supports a simple form of circuit mapping, which I will discuss next. The goal of circuit mapping is to transform a circuit to satisfy the connectivity constraints of a target architecture. Architecture connectivity constraints are given as a graph that describes which pairs of qubits can participate in 2 qubit gates. For example, in the architecture shown on the left of the slide, a 2 qubit gate is possible between qubits 0 and 2, but not between qubits 1 and 3. To map the program in the center of the slide to this architecture, we need to swap qubits 1 and 2 in order to implement the second controlled knot. We prove that our circuit mapping routine satisfies two properties. First, the output circuit has the same semantics as the input circuit up to a known permutation of qubits. The program on the right of the slide has the same denotation as the one in the middle, provided that you undo the swap between qubits 1 and 2. Second, the output circuit only has 2-qubit gates between qubits that are allowed to interact. In the program on the right of the slide, 2-qubit gates occur between qubits 0 and 2, 1 and 2, and 2 and 3, all of which are valid edges in the given connectivity graph. As an example of using our API, here's a clock function that takes a circuit C and applies our optimizations inspired by NOM, followed by our optimizations inspired by IBM's QuizKit, and finally maps C to a 10-qubit linear nearest neighbor architecture. This clock function can be verified and extracted to executable OCaml code, or we can write this function directly in OCaml, making calls to our verified library functions, optimize NOM, optimize IBM, and simple map. Here's a function that applies the transformations in the reverse order, mapping first and then optimizing. To ensure that this optimization produces useful output, we have formally verified that all of our optimizations are mapping preserving, meaning that they do not introduce 2-qubit gates disallowed by the input connectivity graph, and will not destroy the properties guaranteed by simple map. One thing you might wonder from the previous two slides is whether our optimizations provide any benefit for mapping, and whether it is better to optimize before or after. To test this, we evaluated the effect of optimization on 26 benchmark programs, mapping each of them to a 6x6 2D grid architecture. We report the geometric mean gate count reduction compared to unoptimized mapping for 3 different configurations: optimizing before, optimizing after, and optimizing both before and after. As you might expect, optimizing at both ends is the most effective. It also turns out that optimizing before mapping is more useful than optimizing after, because the optimizations we've implemented so far are not as effective after swap gates have been inserted. One important point is that because we have formally verified that all of our transformations preserve semantics and mapping, we can freely mix and match different VOQC passes without concern that certain combinations introduce bugs. In our POPL paper, we present an evaluation of our optimizations on a much larger set of benchmarks and compare VOQC's performance against other quantum compilers like PhysiX, QuizKit, and TCAT. Our end goal is to make VOQC a drop-in replacement for the optimizers used in existing quantum programming frameworks. Many recent frameworks, like QuizKit, PyTCAT, PyQuil, and Cirq, are written in Python. So we decided that the best way to increase VOQC's utility was by providing Python bindings. To this end, we implemented PyVox, a Python wrapper around VOQC. The path from our verified COC code to the Python bindings is shown on the slide. In summary, we extract our COC definitions to OCaml, wrap the OCaml code in a C library, and then call this library from Python. Here's an example of using VOQC like a custom pass inside of the QuizKit framework. The Python code on the left produces the output shown on the right. In this example, we are showing the effect of running our NOM and IBM optimizations on a small input circuit. This code is an excerpt from the tutorial available in our repository, for which I will provide a link at the end of the talk. There is still plenty left to do. One near-term goal is more thorough benchmarking, both to evaluate VOQC's current optimizations and also new optimizations moving forward. In particular, we have been looking at integrating VOQC into Arlene's benchmarking toolchain. In terms of new optimizations, we are especially interested in implementing and verifying approximate optimizations, which do not preserve semantics exactly, but instead produce a circuit with the semantics close to the original. We are also interested in more sophisticated mapping routines and optimizations targeted at reducing the swap gates inserted by mapping. One of our main projects, led by my co-author Li Yi, is adding support for compiling classical reversible functions, like arithmetic circuits, to efficient Swire circuits. Our code is freely available on GitHub, and we welcome contributions and feedback. If you are interested in our formal proofs, then you should look at the Swire repository. If you are interested in using Vox, then you should check out the MLVox or PyVox repositories, depending on whether you want to use OCaml or Python. Thanks for listening. We're looking forward to feedback on the direction of Vox and ideas for moving forward.